Hello friends, today in chapter 6 application of derivative we will study about maximum and minimum value of the functions. So we have many functions like profit functions we can give px is equals to ax plus bx square. Then we have interest in what is the minimum profit and which is the maximum profit. Same way we throw some object and what height it will reach. So like this way we have many functions like if we throw object it gives us the parabolic function, so x square plus 7 we can take. So like this way there are many we have polynomials and functions which gives us the maximum and minimum values. So at which value it is maximum and minimum, that today we will study through application of derivative. So we know that if c belongs to I, is some integer or some number from interval I, then for given function fx, if fc value is greater than or equals to fx for all x belongs to I, then fc is called the maximum value. And same way if fc value is less than or equals to fx for all x belongs to I, then fc is called the minimum value. So in the interval I, for all values of x we find out fx. In that c is a number such that fc value is greater than from all the other values or is equals, then we can say that fc is the maximum. And if fc is the smaller than from all the other values, then fc is called the minimum value. Then c is called the extreme point where it shows the maximum and minimum of the values. So now we discuss about maximum and minimum of fx equals to x square. So we draw the graph of fx equals to x square, then we know that the graph at x equals to 0, it is 0 and it goes on increasing in both the intervals for the positive and negative values in both the parts. And so at x equals to 0, fx equals to 0, which is minimum value for all x belongs to R. And so the fx equals to x square has the minimum value 0, but the f1 is greater than f0, then f2 is greater than f1, and so each value goes on increasing and increasing, and so maximum value of this graph we cannot decide, and so fx equals to x square do not have the maximum value but its minimum value is 0. Same way we take fx equals to modulus x. Then we can see the graph of the modulus x. For the positive values it comes near the 0 and like this way. So at x equals to 0 its value is the 0, where other values it is positive, so 0 is the minimum value, and so fx equals to modulus x as the minimum at x equals to 0, but it is also increasing in both the direction, and so as x value changes, and so we cannot decide the maximum value for fx equals to modulus x, and so fx equals to modulus x do not have the maximum value but it has x minimum value at x equals to 0. Now we take fx equals to x belongs to closed interval 0 to 1 we take, then f0 equals to 0 is the minimum value and f1 equals to 1 is the maximum value. But instead of closed interval we take it as open interval, then 0 and 1 are not included. So if we take that fx0 is the smallest value, then x0 by 2 is less than x0, and so nearest 0 to value we are not getting, and so it do not have minimum value, as well as nearest value to 1 we take that x0 is the greatest value nearest to 1, then x0 plus 1 by 2 is more greater than that, and so like this way the values are goes on increasing, and the 0 and 1 are not included, so we cannot say they are maximum or minimum at any value. So here we can say that every continuous function has a maximum or minimum value. So here one of the continuous function graph is given. We can see that first it decreases, and at a point it becomes the minimum, then again it starts increasing, and at b point it becomes the maximum, again it starts the decreasing, and at c point it becomes the minimum, again it starts increasing, and it becomes the at d point maximum. So here we can see that a and c are showing the lowest point, and b and d are showing the highest point, and so at a and c they are the minimum values, at b and d there is the maximum values, but here they are increasing decreasing for some intervals only, and so f is any real function, then c belongs to interval I of f, then there exists smaller value h such that h greater than 0 such that fc is greater than or equals to fx for x belongs to c minus h to c plus h. Then fc is called the local maximum values, and if fc is less than or equals to fx, then we can say that c is local minimum value at f, and again we can say that if c belongs to I and h we get small h greater than 0, means h is the very smallest value for which if the interval x belongs to interval c minus h to c plus h, and fc value is greatest value for all other from all other x, then fx, then we can say that fc is the local maximum value of f, and fc value is smallest value from all other fx, then we can say that fc is the local minimum value. Now we have studied here at f dash c is the 0, as c is the maximum value, so graph is going on increasing, and so increasing decreasing function we have studied that when the function increases f dash x is greater than 0, and when the function is decreasing when the f dash x is less than 0, and at extreme point f dash c must be 0. Same way when function is decreasing function, then at the c minus h to c interval the f dash x is less than 0, and c to c plus h interval f dash x is greater than 0, and here c minus h to c function interval f dash x greater than 0, and c to c plus h f dash x is less than 0, and so we can say that if fx and c is the maximum value, then in the first interval c minus h to c f dash x is the greater than 0, and c to c plus h it is less than 0, and fc is the minimum value, then we can say that in c minus h to c f dash x is less than 0, and c to c plus h f dash x is greater than 0. So here at x equals to c it gives us maximum and minimum value, so it becomes the extreme point, and at our extreme point f dash c must be 0, or f is not differentiable at x equals to c. So through this we can see here we have studied that f dash x is greater than 0 in c minus h to c, and f dash x is less than 0 in c minus c to c plus h. Then fx has the maximum value, means when it's c equals to at x equals to c we have maximum value, then in the left side f dash x is greater than 0, and right side as we go f dash x becomes less than 0, then at x equals to c we can see the maximum value. And similarly when we go in the function, when at x equals to c it is the minimum, then we have studied f dash x is less than 0 in c minus h to c, and f dash x is greater than 0 in c plus to c plus h, means as f dash x becomes less than 0 in left side of the c, and f dash x is greater than 0 in right side of the c for x belongs to this interval, then we can say that at x equals to it has the minimum value, and if it is neither increasing nor decreasing, means there is no local maximum, local minima, and such point is called point of inflection. And so we have the first derivative test. If f dash x changes from positive to negative, then at x equals to x increase through c, then we can say that the fx has the local maxima at x equals to c, and f dash x changes from negative to positive as x increases through c. Then we can say that fx has the local minima at x equals to c, and if f dash x does not change the sign, then it do not have neither maxima nor minima, and such point is called point of inflection. Now we have the question, find local maximum values and minimum values of fx equals to x cube minus 3x plus 3. So we differentiate with respect to x, f dash x equals to 3x square minus 3. Then f dash x equals to 0 we take for the critical points. Then 3x square minus 3 equals to 0. So x square minus 1 equals to 0. And so we have f dash x equals to 0, 8, x equals to 1, and x equals to minus 1, as x minus 1 into x plus 1 equals to 0 here. So x equals to 1 and x equals to minus 1 are critical points for us. So we check it by first derivative test, then very close value of the right side of 1 we take, means f1.1 we take, and it is f dash 1.1 will be 3 into 1.1 square minus 3. which is 3 into 1.21 minus 3, so 3.63 minus 3 greater than 0, and f dash, if very close value to 1 to the left side we take, then 0.9, and 3 into 0.9 square minus 3, so 3 into 0.81 minus 3, which is 2.43 minus 3 less than 0. And so we can see that for one right hand side f dash x is greater than 0, and for one's left hand side f dash x is less than 0 for very close value. And so if x equals to 1, it has the local maximum value. So similarly for x equals to minus 1 we can check, then f minus 0.9 will be less than 0, and f minus 1.1 will be greater than 0 for x equals to minus 1. And so in the left side it is less than 0 and right side it is greater than 0, and so we can say that x equals to minus 1 is the local minimum value. X equals to minus 1 is the local maximum value, and its local maximum value f minus 1 equals to minus 1 cube 3 into minus 1 plus 3, and so it is 1 plus 3 plus 3, 7. Now we have the example 30, that fx equals to 2x cube minus 6x square plus 6x plus 5 has local maximum or local minimum find. And so f dash x we take, that is 6x square minus 12x plus 6. So 6 we take out common, then x square minus 2x plus 1. And so it is 6x minus 1 square. And so we have extreme point x equals to 1, for then f dash x equals to 0. But for for any value of x belongs to, either we take x very close to 1 to the left side or right side, f dash x is always greater than or equals to 0. And so here we can say that either left side or right side f dash x is always greater than 0 by first derivative test. X equals to 1 is neither giving local maximum value and not a minimum value, and so x equals to 1 becomes a point of inflection.